wrongfully exempted from their official responsibilities to file such statements. The report, backed by both public and private agencies, may make the integrity of the federal government an early priority for Congress. After this message, we'll be back with sports, the weather, and details on tomorrow's earthquake.
Of all the sudden natural forces on Earth, the one that has been most destructive is the one that has come most unexpectedly. This force is the earthquake. In some ways, the earthquake is a gentle force. Simple shaking of the ground has rarely hurt anyone. The danger comes from falling debris, fires, landslides, and seismic sea waves, popularly known as tidal waves. If we could accurately predict when and where the next large earthquake would occur, dams could be lowered, gas mains turned off, emergency crews alerted, beaches and unsafe buildings evacuated, and thousands of lives could be saved. In the past, earthquakes were explained by myths. Fires burning in the earth, giant catfish, even giant elephants and turtles. A more scientific approach starts with the simple observation that there are zones where earthquakes occur frequently. We now know why. The answer has a history dating back to 1620, when Francis Bacon, studying a map of the world, noticed that the coastlines of North and South America and Europe and Africa were quite similar. 300 years later, a German geographer named Alfred Wegener noticed the same thing. But he took the idea a step further, proposing that at one time all continents were together in one landmass. Over millions of years, they slowly separated and drifted apart. A clever idea. But how this happened was not known until the ocean floors were mapped. Right in the middle of the Atlantic is a mountain range called the Mid-Atlantic Ridge. Here the sea floor is spreading. Molten lava is pushing up, forming new crust. The Pacific Ocean was also mapped, revealing trenches. Here the crustal plate is slipping back down into the earth. If a continent happened to be part of this moving plate, it would move along with it. Using the ridges and trenches as boundaries, the earth can be divided into 10 major plates, all slowly moving on the earth. It would be safe to predict that the next large earthquake would occur along the boundary of one of these plates. In California, 2 crustal plates are moving past each other. The Pacific Plate, including Los Angeles and Baja, Mexico, is moving northward in relation to the North American Plate. The speed is only about as fast as a fingernail grows, but in 10 million years, Los Angeles will have moved north next to San Francisco. The name given to the fracture dividing the 2 plates is the San Andreas Fault. In Hollister, California, the fault runs straight through the middle of town, bending the curbs and sidewalks, twisting the fences. In most places, however, The fault is locked even as the plates continue moving. Gradually, strain energy accumulates until it exceeds the strength of the rocks. The rocks break, and there's an earthquake. The energy is released in waves moving out in all directions, similar to the waves formed by a stone dropped in water. These waves can be detected by an instrument called a seismograph. Seismographs come in various types and shapes, but they all work on the same principle, a suspended weight. While the ground and the rest of the instrument shake, the weight remains steady, recording the amount of movement. There are different types of earthquake waves. The first, detected by a seismograph, is called a P, or primary wave. This wave travels with a push-pull motion through the ground. The P waves are followed by S waves, or secondary waves. The S wave travels sideways through the ground with a speed almost half that of the P wave. The speeds of the P and S waves are important in finding where an earthquake originated. If we know the speed and the difference in arrival time of the two waves, the distance to the earthquake source can be plotted. With 3 seismic stations, the origin or epicenter of the earthquake can be found. The last waves detected by a seismograph travel only on the surface of the Earth. For this reason, they are called surface waves. Surface waves and S waves are the waves usually felt in an earthquake. Although the San Andreas Fault is the largest fault in North America, there are thousands of others. Smaller and not all breaking the surface, many of these faults have also released damaging earthquakes. In fact, over this century, most states in the continental United States have had earthquakes. These were the quakes that people have felt. There were thousands more detected only with a seismograph. Recently, it was discovered that seismographs can do more than detect earthquakes. The information they record, properly interpreted, can warn us of future earthquakes. Earthquakes happen all the time. Radiating out in all directions, the waves often pass through other faults before being recorded on a seismograph. In studying seismic records, scientists discovered an interesting pattern. The P waves from various earthquakes in the area would slow down. Then later, the P waves from other earthquakes would return to normal speed. Soon after that, there would be an earthquake here. What makes this discovery even more interesting is that the period of reduced wave speed can tell us how large the upcoming earthquake will be. If the period occurs over a few days, then a small earthquake will follow. If over a few months, then there will be a medium earthquake. If over years, well, other methods of earthquake prediction have also been explored. One is the tilt meter. This highly sensitive instrument can detect minute deformations in the Earth's crust. A slight tilt has frequently been observed just before an earthquake. Another approach to earthquake prediction is the study of surface uplift. The ground has been known to slightly elevate before a quake. Deep wells near a fault are a source of another predictor. The water level in these wells has been found to change just prior to an earthquake. Strange animal behavior has even been observed before some quakes. One theory has been developed to explain some of the changes observed before an earthquake. The theory is called dilatancy. It states that as a rock accumulates energy, it will crack. The cracks expand and the rock swells or dilates. This increase in size could account for the uplift or elevation of the ground. Also, P waves passing through the rock would slow down. P waves do not travel as fast through cracked rock as they do through solid rock. The ground uplift and the reduced wave speed are the first warnings that an earthquake is on its way. The second warning comes later, when groundwater seeps into the cracks. This could account for the change in water level in wells. Also, the P waves would resume their normal speed, as they travel faster through water-filled cracks than through empty cracks. The water has another effect. It weakens the rock. This, together with the ever-increasing strain, is enough to break the rocks, causing the earthquake. One of the best early attempts at earthquake prediction was made by the Earthquake Research Institute in Japan. In 1966, the town of Matsushiro was experiencing an earthquake swarm, sometimes as many as 6,000 earthquakes a day. Scientists set up an array of instruments, including surveying equipment, seismographs, and special water-filled tilt meters. A photographer's team even set up cameras. In analyzing their data, scientists discovered that just before a large quake, the tilt meters would show a sudden change. And there would also be an increase in micro-earthquakes. In August of 1966, one side of a fault elevated 20 centimeters in 20 days, indicating the imminent approach of a strong shock. Following close to these shocks, the town was struck by disaster. A landslide started. A great mass of earth pushed downward. In all, 11 houses were destroyed and 150 acres of orchards were ruined. Thankfully, no one was hurt. The people had been led to safety by members of the Earthquake Research Institute. In conducting their research, earthquake scientists have a few problems which other scientists don't normally have. For one, people are living in their laboratory. There's another problem. Despite the advancements in understanding the mechanics of earthquakes and in the technology of measuring earthquakes, and despite the fact different signs have been found to occur before an earthquake, it is still difficult to understand what is happening far below the surface. Mistaken predictions will surely be made. Even so, the responsible scientist will make a prediction when data show that an earthquake is imminent. Dams could be lowered, gas mains turned off, emergency crews alerted, unsafe buildings evacuated. Lives could be saved.